So this is Tucker Goodrich and David Gornosky, who is on the road and couldn't make it to us this morning. But I am here with Ameer Taha, who is an associate professor at the University of California, Davis Food Science and Technology Group, where his specialty is looking at oxidized lipids and lipid-like environmental toxins, such as pesticides and antibiotics in the food supply. He's done a lot of really interesting research in the area of omega-6 and omega-3 fats in health, and how, if I could summarize it up, a non-evolutionary level of these fats may have implications, positive and perhaps negative, on our health. Welcome, Ameer. Thank you very much for joining us today.
Thank you for having me.
So perhaps you could explain a little bit about how you got into this line of work. I know you started up in Toronto with Stephen Cunnane working in his lab. Is that correct?
Yes. So I was, for a long time, I was interested in lipids. The interest was actually sparked by my third-year university biochemistry professor, Dr. Roy Baker. So after taking his difficult class, I wanted to get some hands-on research experience on lipids and how they are metabolized and their role in health and disease. And one of the things that fascinated me about my former dear mentor, Stephen Cunnane, was his interest in understanding how this high-fat ketogenic diet can be used to treat epilepsy in kids with drug-resistant epilepsy.
Treat epilepsy, that is.
Right. So the diet can be used to treat in some kids epilepsy, or reduce seizure frequency significantly in in kids who have drug-resistant epilepsy. So that was known, and he was exploring the mechanism. And the ketogenic diet, as some folks would know, is about 80% fat, and 75 to 80% fat, 16% protein, and 4% carbohydrates. So I joined his lab to explore that angle, to understand how, what the ketogenic diet was doing to whole body metabolism. And that sort of linked me, or tied me, into brain research, looking at the intersection between lipids and brain research. And from there, it was a non-ending story.
And that's a really interesting field, because my understanding is we still don't entirely know what the mechanism of the ketogenic diet is for epilepsy, although we do know that it can be quite effective. I have a friend who it was basically a miracle cure for, after decades of suffering with seizures. She's now completely seizure-free and has been for years, and is off all of her drugs. So I mean, that's pretty remarkable therapy.
It is, yeah. And there's likely more than one mechanism involved. We were exploring this hypothesis that with the ketogenic diet, you have some mobilization of the anticonvulsant or anti-seizure fatty acids, such as docosahexaenoic acid. You mobilize them from adipose, and they accumulate in the brain. And we showed some evidence of that during my time in Dr. Cunnane's lab.
Interesting.
And then I went to Dr. Mac Burnham's lab at the Department of Pharmacology and Toxicology at the University of Toronto, where I looked at the effects of docosahexaenoic acid and seizure resistance.
Interesting. Yeah, Professor Cunnane was wondering if you're ever going to get back to looking at the change in DHA metabolism in rats on a ketogenic diet.
I'm hopeful that I would go back to it. I think we started a nice, interesting story, and it was because he moved to Sherbrooke at the time, so he just left me hanging in there, and left me hanging with my passions.
I see.
But now it's that I'm a faculty, I should try to go back to it.
Interesting. Well, I'm sure he'll be happy to see that. He seems to be curious on getting an answer out of that line of work. So you've also worked with fellows at the National Institutes of Health, Joseph Hibeln and Christopher Ramsden. Can you describe a little bit of the work you've done down there?
Well, when I joined the NIH as a postdoc, I worked with my primary mentor was Stanley Rappaport, and through him we were working with Joe Hibbelin and Chris Ramsden. And I was working primarily on lipid signaling in the brain. We were, Dr. Stanley Rappaport has developed this nice method, pardon me, to understand how this radio tracer method, to understand how the brain during dietary manipulation or genetic disease and so forth handles fatty acids. And that's what I was working on, looking at brain lipid signaling in animal models of brain disease and so forth. And this sort of also led to the interaction with Chris Ramsden and Joe Hibbelin in our work on the linoleic acid story.
Interesting. And they've done quite a number of papers on that. You've been a co-author on a number of them. I mean, one of the papers that you've done that I found was most interesting was one back from Kinane's lab, when you found that lowering linoleic acid in the diet increased omega-3 fats in the body, even if you're not supplementing them, which suggests to me that there's some sort of crosstalk or collateral damage going on. Have you ever thought about what could be the mechanism behind that?
So this was actually when I was in Stanley Rappaport's lab, and this was our collaboration with Chris and Joe. We were primarily working on the preclinical studies, so we had a similar project going on in animals, and Chris and Joe happened to be leading the clinical arm, the clinical studies in humans, and that's when we all got married, basically. to translate rat to what we're doing in animals to humans, which is really important. And in that paper, it was a 2014 paper, I believe, we showed that when you lower linoleic acid, reduce it from 7% energy to about 2%, the plasma omega-3 concentrations increased significantly in humans. If you gave those subjects, if you supplemented them with fish oil, it further increased. In the beginning, we thought it was because of enzymatic competition. So let me explain what this means. It is thought that enzymes, we have liver enzymes that convert linoleic acid to arachidonic acid, and the same enzymes convert alpha linolenic acid, which is an omega-3 fatty acid, into docosahexaenoic acid and docosahexaenoic acid, EPA and DHA, the stuff you find in fish oil.
In fish oil, right.
And at the time,
those processes don't work all that well, and it's sort of a bottleneck, isn't it?
Well, that's what we thought initially, but Richard Bazinet from the University of Toronto proved this wrong. So initially we thought, just because we removed linoleic acid, the enzymes had more access to alpha linolenic acid and therefore converted it to EPA and DHA, docosahexaenoic and docosahexaenoic acid. But Richard discovered that it was a turnover problem. So once you removed linoleic acid from the background diet, the utilization of docosahexaenoic acid was basically slowed down, and therefore it accumulated. From what I recall from that nice study he did, it therefore accumulated in the blood. He showed that in preclinical models, and I think that serves as a better explanation for what we're seeing in the humans.
So the turnover slowing. Well, it's interesting then to speculate why the turnover could be slowing down. I know it's can replace linoleic acid in some roles in the body, like in mitochondria.
Well, I think once you remove linoleic acid from the system or reduce it significantly, you sort of remove a lid on omega-3s and adipose, going from adipose to blood or from liver to the blood, and they start to finally get a chance to breathe and circulate and start to circulate. And the body has the regulation of DHA is quite tight, so when the body sees it has a lot, finally we're releasing these good fatty acids, it says, okay, let's we don't need to make them much, let's take it easy, and I'll hang on to what I have here.
Interesting. So you've also worked a little bit on, we spoke to Bruce Hammock quite a while ago, who's one of your colleagues down there at UC Davis, and he had asked for you to participate in that conversation. Unfortunately, you weren't able to make it, and we did chat with him and Bruce German, and then again with Bruce German on his own, talking about some of his interest in breast milk and human feeding. And you've sort of been looking at that same topic coming from your own particular angle. I mean, one of the studies I think would be real of interest to people is you've looked at pesticides in human breast milk, which is of great concern to a lot of people who are looking for healthier foods in their lives. And you developed a new method to determine what sort of pesticides are in human breast milk. Do you want to talk about that a little bit more?
Yeah, sure. So yeah, as you said, Bruce Hammock and Bruce German are just down the street, and it's really hard to exist in UC Davis without working with these amazing scientists. So it's been a pleasure for sure. So our work in breast milk, this was actually sparked by a small pilot grant that I got from what we call the P30 NIEHS training, not a training, P30 center grant, NIEHS center grant to UC Davis. At the time, so one of the main, contributions of folks here from the Department of Public Health and Department of Medicine is that they've linked exposure to pesticides in early life to problems in infant development. And when I came in, I thought, it would be good to measure these compounds to know, what pesticides are involved and at what concentration, because I do think there's always a threshold at which it matters, and there's a level at which it really doesn't. So we don't really need
the dose makes the poison.
The dose makes the poison.
Right.
And we do a lot of mass spectrometry. I was looking up the methods, and I realized, my God, they are just so like if I were to do 100 samples, it'll take forever, and it would be so expensive. Because the current methods utilize 40 mils or to 100 mils of solvent per sample. You need a lot of breast milk to extract the pesticides from, and it's just a tedious process. You need an army to get it done. So I worked with Teresa Peterson, actually the first author on that paper, to sort of dumb this down. Let's make this simple. And we succeeded in doing so. We developed a two-step simple method for extracting these compounds. So instead of using 40 mils of solvent, we're using 4 mLs, 40 to 110 mils of solvent. We're using 4 mils, which is also, you can see it as also environmentally friendly, because all of these solvents end up being dumped,
probably pretty nasty chemicals on their own.
Nasty chemicals.
Yeah.
And once we relieve that pressure of the measurement pressure per se, we went ahead and worked with Jennifer Smilowitz and others at the Department of Public Health. So Debbie Bennett, Irva Hurst-Picciotto, Rebecca Schmidt, and others. And we worked to ask the question, well, what's in breast milk and how much? So we did survey.
As far as pesticides go, specifically, right? Yeah.
Exactly. Yeah. So we developed this nice method that targets 29 pesticides used primarily in California, and California used in agriculture here routinely. And we were able to detect about 11 out of 29 compounds in human breast milk. And the levels were variable. It was all over the place. But
okay, that's not good.
Yeah, I guess it tells you some folks are exposed more, some are exposed less, and some compounds were seen in roughly up to 80% of the sampled, the surveyed breast milk. But I just want to point out that this doesn't mean we should switch to organic foods right away, because again, the question is, we need to address the so what part, right?
Yeah, exactly. And of course, organic foods have their own group of pesticides that you can use there.
Right.
I mean, I've understood some people saying that one of the disadvantages of organic foods is that you're often using older pesticides and not newer pesticides, which were designed to be improvements, which is a whole off-topic topic for us. I mean, it's interesting, and it's fascinating that hopefully your process will lead to better testing and better understanding of what's going on with this field.
Well,
I
that's
guess
the
that's
next
what,
step,
yeah,
and that's what we're waiting on funding to get through for us to really address that question. Which pesticides and at what level do they are related to, if at all, to neurodevelopmental problems? You know, whether it's autism or social and other behavioral problems during early life. And
right,
that's the $1 million question we have to address. And then
right.
from there, we can translate that to recommendations. Well, maybe you should, you know, dampen it a little bit on this type of food because of X and Y exposure, or maybe not. Let's, you know, I just would like to know the answer.
Right, and I presume that, you know, if pregnant women have these concentrations, then most likely all the rest of us do as well to some degree.
So this would be when we started with breast milk. So this would be lactating women, and of course, you know, it's coming from the blood. And the idea is that yeah, there's likely exposure during pregnancy, and hopefully, you know, we'll try to go back at some point and look at maternal blood to see if it matters or not.
Right.
But you're right. You know, these things are everywhere. It's, you know, the cornerstone of modern society was to use pesticides. We have to live with these compounds. We just need to know how much matters and what matters, and that's how it goes.
Right. So
It's not an
now,
all or none type of deal. You know, we should just eliminate them because we'll starve if we do, and
yes, that
we
would be
just need
rather
to titrate.
impractical.
Yeah, it would be just impractical.
Right. So now, uh, your research on linoleic acid is, some could argue, along the same lines. I mean, obviously, you're working on lipid-based pesticides as well as linoleic acid. That's from, as I said at the beginning, from an evolutionary perspective, that's been the biggest change. I mean, everybody cites the, forgive me if I don't say the name correctly, Blasball 2011 paper out of, you know, that's the
Yeah.
biggest change that's happened in the human diet over the last 150 odd years, has been the increase in linoleic acid. Do you want to, why does that topic continue to interest you and your colleagues in that enterprise of trying to figure out how that's affecting us, that change?
So, like you said, there's been you know, up to at least a threefold increase in dietary linoleic acid in the food supplies, which progressively started to increase from the 1930s onward. The Blasbal paper goes all the way to 1999, but there's been recent papers showing that we're still at, you know,
1899.
1999, sorry.
Oh, sorry, it goes up to 1999.
Up to
Okay, right.
1999, yeah. But there's been more recent papers, including our work with Chris Ramsden, showing that, you know, most people are consuming at least 7% linoleic acid per day. It's really hard to avoid because it's everywhere, mainly, you know, due to soybean oil consumption, followed by corn oil and other types of the so-called, you know, seed vegetable oils, which are seed oils.
Right.
So my question, and also Chris Ramsden, I guess, for, you know, has been asking the same thing. What does this mean? I've been interested primarily on what it means to brain development, to different periods of life. You can, you know, stratify them into development, adulthood, and aging.
Right.
And we're sort of finding different outcomes depending on when you look at it. And we still don't have a conclusive story, unfortunately. But at least to say that linoleic acid is a precursor to a lot of pro-inflammatory lipid autocoids, as they call them. There's so many names for these metabolites. They call them lipid autocoids, lipid mediators, etc. And
Yeah, I saw a talk by, I think his name was Simon Dial, a lipid scientist out of the UK, and his comment was, we're still discovering things, and the whole picture is so complex, it's probably impossible for a human to understand the whole thing. So I guess you're trying to figure out what the important threads going through this biological process are.
it'll be nice if we all agree on a name for these compounds. Yes. You know, we call them OXLAMS, oxidized linoleic acid metabolites.
Does that include 4-hydroxy-2-nonanol or not? I've never quite gotten a straight answer out of that one.
That's no, it's not considered an OXLAM per se. So it doesn't include it, no.
Okay.
But but because they're precursors to pro-inflammatory lipid mediators, so they're called mediators because they mediate inflammation in the body. We're finding, for instance, in adulthood that if you lower, and this is in preclinical models, and it's sort of consistent with what Chris Ramsden has found in humans with migraine, whereby if you lower linoleic acid and further supplement with omega-3s, you can alleviate migraine symptom, headache frequency, and with drug-resistant migraine. In preclinical models, we're finding that when you remove linoleic acid from the diet, you actually increase resilience to inflammation, to brain inflammation. And that has, and I think that's an important thing to think about, at least, especially since it seems to translate to the human side, where if you think of migraines as a process where you have underlying chronic inflammation.
Right. Right. Then yes, obviously eating something that would bias you towards inflammation would probably not be the best idea.
Right. And the other thing is we're finding also, on the one hand, with too much linoleic acid, you do two things. One is you increase these OXLAMS or pro-inflammatory lipid mediators, however you want to call them.
We can stick with OXLAMS. I'm happy with that one.
On the other hand, you tend to decrease some of the lipid mediators coming from docosahexaenoic acid and eicosapentaenoic acid, which are anti-inflammatory.
The omega-3s.
The
right.
omega-3s, and they resolve inflammation.
Right.
So I think you're getting two bad deals in one, basically.
Interesting. So now a couple of thoughts on Ramsden's work. He's done a number of different steps in this process of trying to understand this. And I thought one of the most interesting parts about I think it was his most recent paper, is that he commented that the dietary intervention wasn't as successful as they were looking for it to be. And I guess that was because they were still using some kind of oil in the diet, and they weren't able to get the levels down as low as they were hoping. But nevertheless, they saw an effect that they said was more than most of the drugs that are used to treat migraine.
Right, correct. And from what I understand from that paper, which just came out, so I've yet to look at it thoroughly, it seems, I guess they had some, like I said, it's difficult to lower linoleic acid in humans because it's everywhere. And I think they faced that challenge when they were doing their study.
Yeah, interesting. But nevertheless, they had a significant result. I mean, that's really quite.
Yeah, I mean, it shows you that even a little, a bit of lowering is good, and it helps, especially where the drugs can't take you further towards, the pain relief.
Yeah, well, I've suffered from migraines myself, and my ex-wife did as well, and got to spend enough time with a neurologist to know that in general they don't really have any good answer. It's sort of like, they'll throw different things at you until something maybe gives you a benefit for a little while. And we found that treating it via diet and removing dietary triggers, which I won't get into here, was a huge benefit. So I'm not at all surprised to hear that his study has panned out the way it has so far. Interesting. Now, you've also looked at another paper that you did. One of the things that I found most interesting in kind of the scientific literature about omega-6 fats has been the area of total parenteral nutrition. And you did a really interesting, you were an author on a really interesting paper looking at that in prenatal infants in Australia and Japan. Can you describe to a little, I mean, I know that was very preliminary and they were little babies, so you can't really tell anything about how they turned out in life. But tell us what you found there. That was quite surprising, I thought.
Yeah, that was an interesting study with Bob Gibson from Australia, and I think the take home was that when they gave the infant formula containing different and or certain fatty acid levels, basically the baby used them to converted them into these lipid autocoids, whether from linoleic acid or eicosapentaenoic acid and docosahexaenoic acid. So the take home here is that this gives you an opportunity to modify. So there's two conclusions. One, baby can make these things. and especially the preterm infants getting these compounds. And the second thing is we ought to try, and this is something we've been working on also. We should model this in human breast milk to see what's the optimum,
Right.
not just the fatty acids, but what are the lipid auricoids in the breast milk itself that are being delivered to the baby, and we can sort of translate that to the infant formula in a manner that optimizes the delivery in at least the good lipid auricoids, such as those from the docosahexaenoic acid and icosapentaenoic acid. Linoleic acid is used as a base in these formulations, infant formulations, and I'm not in a position to say it's good or bad because I just don't have the data. And also,
Are you
development.
Are you familiar with Kathleen Gura's work at Boston Children's Hospital?
No.
Okay, she's done a lot of work on that. She convinced the FDA to get rid of the black box warning used on these infusions when it's when you replace a seed oil containing infusion with a fish oil containing infusion. So yeah, they were using intralipid, which it sounds like is the same as the intralipos Japanese formulation that you were using, a soybean formula, and discovered some pretty consistent negative results that resolved, liver failure that resolved when you replace the soybean formula with the fish oil formula. Anyway, kind of outside that. And, what I found interesting about what you were looking at there was that Japanese infants, you would think, would have a better fatty acid balance than Australian, and they did when they were initially delivered. I mean, these were preterm infants, so one assumes that would be the same as if they were naturally delivered. But then they very quickly shifted their fatty acid balance based on this soybean infusion.
Right. Yeah. And I guess where I was going with, not being in a position to comment on it, just because I focus mainly on neurodevelopment. So on the brain side, I don't have an answer. It's something we're investigating now through an NIH-funded project, and I just don't know. I don't have an answer to it. I do concede that some OXLAMS actually, at least in cell culture, they make neurons grow bigger, and some don't. But we got to look at the totality of the evidence in vivo, at least in the, whether that's in the animal itself or in the human itself. And that's what we're trying to understand now. Just see how these things interact with the neurons and what are they doing to brain development overall. And we're doing this work in collaboration with Dr. Pam Lyon at the Vet Med School.
Interesting. And you said you've also looked at some aging-related cognitive dysfunction and the like. Do you want to describe what you found with that work?
Yeah, so we're finding, and this is in collaboration with several people, including Dr. Walter Swartvager from Sunnybrook Hospital in Toronto. We're finding that a lot of the linoleic acid, these OXLAMS, they seem to to impact cognition in a bad way in the elderly. And the mechanism seems to be related to this, to Bruce's enzyme, Bruce Hammock's enzyme, the soluble epoxide hydrolase enzyme, which seems to grab linoleic acid epoxides and convert it to diols, linoleic acid diols, which are pro-inflammatory.
Well, this was the molecule that was originally described as leukotoxin diol.
Right. Yeah, leukotoxin diol. Exactly.
Right.
By Bruce Hammock. Yeah.
Right, which was the original conversation I had with him about that and COVID-19. But that's like most of the rest of these things, and it's kind of important to note that is these are all natural parts of your body. They're all produced in your body normally. I think leukotoxin diol is used to stimulate brown fat operating, which is kind of funny, but the body does nothing if not reuse things, it seems. So it's more like
you said, the dose determines the poison. I think these things are good at a certain level, but in excess and for a long time, and depending on the period of life, they may not be so great.
Right. So you're suspecting that perhaps excess exposure and production of these chemicals that can be toxins at the wrong doses may be driving some amount of cognitive dysfunction, or at least there's
Yes.
an association.
Yes. Yeah. That's what we're showing, and that's what it's been shown also in preclinical models by others.
Interesting. Well, that's concerning. So I, just out of curiosity, what do you do with these findings in your own life? I mean, I personally, about 10 years ago, through a bit of serendipity, decided one day to take seed oils out of my diet and found numerous conditions that had been plaguing me, most notably an irritable bowel disease, resolved in fairly short order. And that's how I got interested in this topic, because many of the things that you're describing as questions in your research, I've experienced firsthand. And I'm just curious, what, the Bruces both gave us an earful on that. I'm kind of curious about what your take is on this. Are McDonald's French fries still your favorite food?
Once in a blue moon, I get those cravings, but chronically speaking, I've always been an olive oil guy. So yeah, it's always been olive oil in my diet. I eat some butter. I like butter, not too much of it, but I incorporate that. I don't use soy. I don't cook with soybean oil. There's been this misconception that you shouldn't cook with olive oil. That's false. That's totally not true.
It's very stable, assuming
it's
not
stable.
Adulterated. Yes.
Yes, exactly. Assuming it's not adulterated, and so Dr. Selena Wang from our department can tell you all about that. But yeah, if it's real olive oil, it's I use it for cooking. It's safe to use for cooking, and it's just fine. So I don't use corn oil or soybean oil for cooking, nor do I add it to salads. I do want to point out though that in the U.S., soybean oil is the primary source of alpha linolenic acid. Also, it's the main source. So and you wouldn't want to go low on that per se, because then you run into having low levels of alpha linolenic acid, which is an omega-3 precursor to eicosapentaenoic acid and docosahexaenoic acid. But there's other sources of ALA or alpha linolenic acid that are also low in linoleic acid. So something like canola oil and others, flaxseed oil if you like it.
And yeah, Gura's group in Boston Health did a really interesting paper. They looked at essential fats over 10 generations in a mouse model, and they didn't give them any of the short chains, only gave them the long chains, and they did just fine. So there's an interesting question about, I mean, they're in every food, so trying to avoid them is kind of a silly thing to do, but it's a big question as to how much you actually need in your diet, I think, assuming you're getting enough of the longer chain fats.
So you mean for alpha linolenic acid?
For both of them, yeah. They gave them
and linoleic acid,
DHA, EPA, and ALA, arachidonic acid, and they did fine over 10 generations. And they were doing this to demonstrate that a fish oil TPN would be safe for human children, that it wasn't going to result in an essential fatty acid deficiency.
Yeah.
So,
but
anyway.
Fish oil does have some of these essential fatty acids anyway.
And yeah, in teeny little amounts.
In teeny little amounts, yeah. And
right.
for babies, you don't need that much anyway. So for babies, for linoleic acid, they need 1 to 2% energy per day, and for alpha linolenic acid, you're at about 0.5% energy per day. So it's really tiny.
Right, and I mean, as I like to say, it's almost basically impossible to become deficient in those unless you're in a lab or under the care of a physician with a TPN solution. That was, I mean, even then, that was years ago when they were having those sorts of problems.
Well, here's the other issue. I mean, even if you were to become deficient, there's so much in adipose tissue that adipose is going to start releasing it. So you're not going to be biochemically, you may be nutritionally deficient, but biochemically, it's going to be a while before you hit biochemical deficiency, because adipose is just going to release them into the blood and you'll be fine for a while.
Which is a pro and a con. I mean, Stefan Guillenet, who got me interested in this topic originally, did a paper looking at adipose levels of linoleic acid over the 20th century. And I think, if I remember correctly, he got most of his data from Hiblin's lab. So that's a, do you think is it worth people being concerned about those high levels of linoleic acid in adipose tissue?
Yes.
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 Oh, drat.
And the way to remedy this is by chronically lowering linoleic acid. I think over time you'll like in our paper in 2014, in 3 months when we reduced linoleic acid from 7% to 2% energy, we found about a 20% decrease in blood linoleic acid levels. But I think if this was to be maintained chronically, you'll start to really lower the blood levels, and adipose is going to try to compensate, because that's what adipose is for. But you're going to get the reservoir, but you're going to get to a steady state, but that at least the supply through the blood to tissues is going to be reduced significantly, to the extent that one may see benefits, just like Chris saw with the headache patients within 3 months.
Right. Interesting. Are there any? I know Professor Kinane did some work looking on, I don't know if you were involved with it, on how linoleic acid and alpha linolenic acid seem to be preferentially oxidized from the diet, which, do you have any thoughts on that and how that might relate to adipose tissue?
Yeah, Stephen, Dr. Kinane, he was doing these studies when this also when I was in his lab. I wasn't involved in the studies, but he was showing that a lot of these the so-called essential fatty acids, most of them undergo recycling, so they get beta oxidized, and then they get utilized to make for de novo lipid synthesis. So they get the carbon, once they're broken down through beta oxidation, they get so beta oxidation, that is, not oxidation in the classic lipid form. So their carbons are then invested into building cholesterol and saturated fats. And I was actually working with him on this recycling pathway back in 2005, and we found that it's almost obligatory for some reason. So even what we did was we loaded the animal with a saturated fat diet, so the ketogenic diet.
Yep.
And we questioned whether recycling is reduced or not from alpha linolenic acid, and we gave a tracer, and we wanted to see if it's reduced or not, and it didn't decrease. It sort of suggested that.
So it's making saturated fat, even though there's more than enough saturated fat. In fact, way more than a mouse would expect coming into the diet.
Exactly. Yeah. So it seems to be like an obligatory pathway for our bodies have evolved as a way to utilize these carbons to make cholesterol and saturated fats, which tells you that these things are important too.
Well, of course, but it also suggests that, I mean, that almost starts looking like a regulatory mechanism where the body is saying, okay, we have enough of this, we don't need it anymore, let's start disposing of it. I mean, similar to what happens when you eat excess glucose.
Well, I think at some point in our evolutionary history, fat was a scarce food, right?
Well, for most of it, right? One would argue, some would
argue.
For
most of it, yeah, for over 99% of our history,
yeah,
our 6 million journey, it's been a rare thing in the diet. And I suspect, even for animals, all the way, back to our, primate ancestors and before that even. So the biochemistry evolved so that it utilizes these fatty acids, alpha linoleic acid and linoleic acid, from vegetables or from animals who eat vegetables. And it's saying, okay, let's just use them to also make saturated fats and cholesterol, which are important for membrane integrity, right? And that's why I think it became sort of an obligatory pathway that these essential fatty acids must undergo and utilize to supply these saturated and fats and cholesterol. Of course, now we have we're exposed to a lot of saturated fat and cholesterol in the diet as well,
Right.
and which we don't need because we have the enzymatic machinery to make these to make them through recycling or other means or de novo lipogenesis.
Interesting. I mean, what that brings to mind is the one of the FADS mutations that was shown to exist in Southeast Asia, where people who, my interpretation of it was that essentially people who were on a vegetarian diet had evolved a superior ability to increase and desaturate the chain length to get the longer chain omega fats that weren't in the diet, since their precursors were all shorter chain omega fats. And there's a mutation there that, again, suggests how important these are.
That's some of Tom Brenner's work, and so yeah, it shows you that we've adapted to our dietary levels of intake. So, and I wonder what fatty acid recycling is like in this population. So, I wish we could study it one day.
Interesting. So that constant stream of fats going into saturated fat suggests that, that while adipose is going to store it, there's going to be a pretty good stream of adipose out on a regular basis, assuming that the same process exists in humans as in the mice that you were looking at.
Say that again. It shows you.
I'm saying that if you're having a constant utilization of these short chain PUFAs, that it suggests that there's going to be a pretty good stream of those going out of adipose tissue if you lower your consumption to a more appropriate level.
Right, yeah, and that's adipose's job. It sort of scans the blood, sees what's there, what's not. If it's not there, it puts it out or tries to maintain it.
Right, but is adipose tissue sensitive enough to determine that there's a need for a specific fatty acid type?
Yeah, it is, and that's one of the things we showed in my first project with Stephen Cunane with the high-fat ketogenic diet. You've changed the blood metabolic environment to the extent that it's high in saturated fat mainly. So you've really lowered the omega-3s, and adipose really kicked in and said, okay, here you go. And they ended up going to liver and then from liver onto the brain. And we were actually able to...
The omega-3s did.
The omega-3s, yes, especially eicosapentaenoic acid and docosahexaenoic acid.
Interesting. So it's a very specific reservoir. I mean, it's not a blob of fat that can actually say, okay, I've got some of this here that you need and send it out into the body. That really is quite amazing, isn't it?
It talks. It talks and does. And they showed it in humans too. So children on the high-fat ketogenic diet tend to have 2 to 5-fold higher levels of omega-3 fatty acids in their blood. And it's through this mechanism. Adipose sort of senses, hey, there is some reduction here, so let me spit it out for you guys. And it does.
Interesting. So, but why doesn't that happen? Well, that gets back into the crosstalk between linoleic acid and the omega-3s, that there's something is suppressing it effectively, is what you're saying.
So the crosstalk, it's DHA that's sort of, so what happens when you lower linoleic acid, for example, DHA sort of gets a chance to pretty much sneak out of adipose and gets output by the liver, basically.
Right.
And then DHA is interesting because it's very it's very regulated. So DHA at a certain level in the blood, once it hits that level, it tells the liver, I don't need more DHA. So you don't need to make more DHA from alpha linolenic acid. So whether that's level provided by diet or adipose supply or simply lowering linoleic acid so that DHA has a chance to come out, peak out and get into the blood from liver and adipose. Once DHA is there, it says, I don't need alpha linolenic acid to go into me again. I just need to maintain my levels. And that's when it slows the conversion of alpha linolenic acid to docosahexaenoic acid. And that's what I mean by, the turnover is altered or slowed down a little bit, basically. And there's a lot of it in the blood that, the tissues, the brain, the muscle has what it needs. So it's elevated, they have what they need, and it's just staying high, it's staying up there. And it trickles slowly to other tissues, but it slows its turnover so to regulate its concentrations because they're tightly regulated. If DHA wants to stay at 5 nanomoles per liter, for example, it's going to really stay there.
Right. Right. Well, makes sense. I mean, arachidonic is the same way, and obviously, lots of things in the
Yes.
blood are staying at constant levels because things
Yeah.
stop working otherwise. It's not surprising that these should too. So you, in our pre-chat talk, you mentioned a couple of projects that you're working on but can't really talk about now. What I'd like to know, though, is what are the things that you would be most interested in working on? I mean, if you had your druthers at this point about, some billionaire came and said, Ameer, I like your work, do whatever your dream project is. And I'm not that guy, so I don't want to get your hopes up here, but what are the things that you'd be interested in working on?
So one thing I really want to see through one day is if we lower linoleic acid in elderly, does that prevent dementia to any extent? Does that slow the progression of dementia? So that's one thing I want to try to see through at some point. Another project, another thing I'd like to do is neurodevelopment. I think it's very complicated, and just looking at these fatty acids and their lipid autocoils or lipid mediators that come from them, including the OXLAMS. I think there ought to. Currently we're focusing mainly on the OXLAMS, but I do want to look at the interplay, the networking between OXLAMS and other, DHA and EPA-derived lipid mediators. How are these things kept in balance during development, and what does it mean? So one of the starking observations we made recently, and we've published it in last year, in fact, Journal of Neurochemistry. We showed that the baby rat brain has half of the oxylipins or the oxidized fats in the baby rat brain are made of OXLAMs. These oxidized metabolites from linoleic acid. When these baby rats become adults, this value goes down to about 5 to 7%. So you go from 50% to 5. So the brain is, in terms of oxidized fatty acid species, is full of OXLAMs in early life, and then it sort of says, okay, I don't need that many now, and I'm going down to 5%, and it stays at 5% for a while. Why is that?
Interesting.
And I don't have an answer. We found that one of these OXLAMs, regulate neuronal morphogenesis. This was with Dr. Pam Line, so it enhanced neuronal outgrowth. And that's where I'm thinking there's some complicated networking, crosstalking between these OXLAMs and other lipid mediators. And they're important they're probably important in early life. And then when the brain develops, it says, okay, I don't need you anymore. So that's why I got to reduce you to certain levels. But then the question is, if I increase...
Well, also, what would that look like on a natural rat diet, not a lab diet?
Right, yeah. So this was on a natural lab diet, which is actually similar to our diet, 7% linoleic acid. And what we're doing right now is we did the study where we lowered the linoleic acid and further increased it to see if we can change these OXLAMs, and we're trying to see what they do to the brain in terms of neurodevelopment. And that's where we want to, answer these questions.
Interesting.
I just think neurodevelopment is a different ball game from adulthood and aging, just to say that.
Yeah, no, exactly. And I should also mention that you wrote one of the more terrifying papers that I've ever read. Congratulations. Your paper kind of doing what you're talking about here, looking at linoleic acid in the brain and some reasons that we might be concerned about our excess linoleic acid consumption. And one of them, as I recall, was IQ lowering.
Yeah. Yeah, there's been some studies correlating linoleic acid in breast milk to IQ and other developmental features in humans. Yep.
Yes.
So that was a bit concerning. And again, it's the question is how much, right? And my guess is at some level they're needed and they're good for you, and it's beyond that, and that's why we see half of the oxidized lipids in the brain made of these OXLAMs.
Right.
But beyond that, they may do more damage than good. And during which period? Pregnancy or lactation or after that? Development is quite a vast. It's a 40-year process, right? Because the brain myelination continues till the late 30s.
Right. Well, yes, we hope.
for some people. So during which period? When is the critical period? And I think that's something we ought to answer. So that's what I would do with $1 billion.
Okay, well, that'd be worth it. One thing that I have noticed, there's a really interesting paper that I came across several years ago, and it was looking at cartilage composition. And they noted that in every single species that they looked at, when the animals were born, both mammals and birds, that cartilage was comprised of a large amount of mead acid. Now, the connoisseur on these topics will say, oh, mead acid is an indication that you're deficient in essential fatty acids. So why is it that every one of these species, when it's born, is sent out into the world deficient in essential fatty acids? That's one of the questions I'm very curious about. And I've, just sort of got to the point to wonder if maybe a higher level of mead acid might be more of a natural situation that, in a natural environment, these fats would be hard to come by, and we might, obviously we have a backup, and maybe we need the backup, but
right.
I don't.
I mean, also, this concept of deficiency, what's deficient for us is different from birds and other, species, other animal species. But I mean, that's why mead acid is created during essential fatty acid deficiency per se.
Right.
It's sort of at least in humans, it's or
A
rats
backup
for that
plan.
matter. It's a backup plan,
Right.
and it's impressive that the system evolved a backup plan. That's a good thing. It's something to sustain you until you find your next food or diet containing these essential fatty acids. But your question, why in birds it may in cartilage?
No, it's in mammals. It's in mammals and birds.
Right. Yeah. So
Right.
why is it higher specifically in cartilage? I suspect there is an evolutionary need for it during that specific period, and yeah, and I don't have an answer to that, but that's my guess basically. It's the same reason why the same question why why are when pigs are born they're born running. When humans are born they're useless pretty much.
Right.
The cerebellum is developed in the pig. And in humans, it's not. It takes a while. It takes its own time. And I guess there's some evolutionary pressures here, where the pig really has to run once it's born.
Well,
if pigs
stood up and had arms, they'd probably have babies who couldn't run either, right?
Exactly. Yeah. So yeah, it's worth looking at these evolutionary pressures and at a biochemical level and functional level.
Well, that's great. Ameer, this has been a fascinating conversation. Thank you very much for your time. I know you have to get off to your next thing today. So it's sadly, David couldn't join us today, but he was very excited to talk to you and was quite disappointed that he wasn't able to make it here. It's been a really exciting discussion. Just by the way, for the audience, he isn't actually at the ASN 2021 virtual meeting. He just really likes the background, and it's kind of cool for somebody who's studying functions of the brain to be standing there in front of what looks like a neuron.
Or an alien.
Or an alien. So again, thank you very much for your time today. It's been a really interesting discussion.
Thanks for having me, Tucker.